Hey guys, so another review video here. I want to talk about population, not human population though, because we just kind of did some free response questions on that, and we talked a little bit about that. Talked about the age structure diagrams, the demographic transition, um, and I think we hit all the main points on human population. So now, in this video here, probably about 10 minutes here, want to talk about a couple things about, I guess we'll call it animal population, other types of organisms in the biosphere, not just humans, and just some main points here. Before I do that, though, and this isn't anything on the screen here, but I'm looking through my notes. I'm kind of just going through my notes and saying, oh, let's review this, just hitting the big ticket items here on these videos, trying to. And I hit indicator species. So when we went to the pond um, at Five Rivers, and we were looking for what type of organisms um, were in the pond to determine the pond health. So I just wanted to throw that out there that there are lots of different indicator species, and some are indicators that the water is healthy and clean, and some are indicators that it is not. We talked about aquatic worms being able to live in a pond or a water source that is polluted. Some other ones that are pretty, um, you know, uh, as far as the names are concerned, it's like, all right, that makes sense. The water is polluted because it has rat-tailed maggots and bloodworms and midge larvae, and they just don't sound clean, right? So those are for polluted waters. They can adapt, right? They have different types of adaptations where they can live in the water even if it's pretty dirty and polluted. Whereas, we joked about the left-handed snail, right-handed snail. The right-handed snail can live in clean water. Nymph, let's see, sorry, stonefly nymphs and mayflies, rifle beetles, and different types of amphibians. If you got frogs living in your pond, that's a good sign. We talked about in maybe streams, dissolved oxygen content. If salmon are thriving, they need a lot of oxygen, so that's good. Trout, let's see, is another good one. If they're there, then it's probably fairly clean. So I just wanted to throw that out there. I know I'm not showing you anything here, but it was just in my notes, kind of right before this stuff. So I saw it, so I figured I'd bring it up again. All right. So, anyways, that's a good thing for scientists, ecologists, people who want to study stream, pond, river health. What's in the water? Are they thriving or not? And that gives you an indicator, right, of the quality of the water. All right, or of the environment there. So, actually, that brings me to this here. So, just I showed you this a long time ago. This has to do with population, right? So, every organism needs a certain set of conditions, and some, like generalist species, their adaptations and their range of conditions is wider than specialist species, right? Or niche species. We always think, or I always think of like pandas, right? They're very specific to what they eat and the conditions and where they live. Koalas, another example, right? So certain fish, certain insects, all types of different organisms have a range of optimum, let's say, temperatures or pH in water, let's say, or foods. And I just wanted to show this to you. It's kind of just a typical bell curve. And the species, for example, the fish here, will thrive in the optimal range here would be in the middle at a certain temperature, certain pH, let's say, so certain conditions. And as you get further away from that, right, temperature starts to increase. Then or temperature starts to decrease, then obviously then this fish can't thrive. And there's certain zones of stress, and they might be able to adapt a little bit here, but then when you get to a certain point, organisms can't adapt, and then they won't thrive, they won't survive. So we did the project on adaptations, and I'm not going to go over all the little details here, but just wanted to throw this out there. Okay, what else do I have here? All right, so this is population stuff. So first, let me just zip through some of these notes. We'll talk about K, R species, and then those survivorship curves. Remember, we went to the cemetery, so we'll hit that, and then that'll be it for this video. All right, so just in the notes that we went over, just understand that there's obviously the entire earth, and then it works its way down to an individual species. And the community is a whole interaction of many different populations of species. The word population typically refers to how many of a certain type of species. Um, so this is just statistics that scientists can keep as far as the overall size, the density in a certain area at a certain time, um, population distribution, just description of how individuals are distributed with respect to one another, males to females, and then as far as the age structure, how many individuals fit in a specific category in a population. Okay, so there's two types here of factors: density dependent and density independent. I do have some examples here. A factor that influences an individual's probability of survival and reproduction in a manner that depends on the size of the population. And then a density independent is one that has nothing to do with the size of the population, right? At any population size. So density dependent. So the size of the population, that would be food, water, clean air, territory size. Because the more people or more organisms, you need more food, need more water, need more clean air, need more territory size in a larger area, whether it's water or land. Density independent, again, factor that has the same effect on an individual's survival and as the population, right? So it doesn't matter the population size. So what we talked about were mostly natural disasters, right? Tornadoes, hurricanes, flood, fire, volcano, drought, heat wave. So all of those will directly affect individuals, and it doesn't matter if we're talking about 1 million individuals or 10, right? If you have a flood or a volcano, it's going to affect the individual in the same way. It doesn't matter how many people, or I keep saying people, how many organisms are in that area that experiencing that natural disaster. Whereas up here, absolutely, the number of people can affect the individual's chance to survive if it's food, let's say, right? So if we're talking wolves or some kind of predator and there's not a lot of prey running around, the individual's chances of surviving goes down the more or the higher the population, right? So that's density dependent versus density independent. Okay. So if you guys remember, we talked about the growth model, the exponential, the J curve, and then the carrying capacity. So we'll get to that in a second. But the exponential, also a J curve, that would be no limitations, right? So there's no limitations on the growth of the population. Maybe it is a organism that has no predator. There's plenty of food, water, land, and that's how it would keep growing. That's the exponential model. But there is usually a limiting resource. So eventually that limiting resource will decrease, right? Resource cannot live without and occurs in quantities lower than a population would require. So eventually it will level off, and that's called the carrying capacity, right? So there's your carrying capacity, right? So this is the logistic growth model where early it's exponential, but eventually that limiting resource is met, and then the population levels out, right? Growth stops. As a result, pattern of population is more of an S curve. So this is more how things actually work, not the exponential, because eventually you reach your carrying capacity. And we talked a little bit about that with humans and Earth. And, are we going to figure it out with technology or what's going to happen, right? Because eventually you reach your carrying capacity, and then parts of the population will have to die because there isn't enough resources. But what happens is you can have overshoots, right? When a population becomes larger than the environment's carrying capacity, that tends to happen with the R selected much more than the K, and we'll get to that in a second. And what you have is a die off, and I have back to that picture here. So there it is, right? So this can happen, especially think of like mice or rabbits or insects. They reproduce like crazy, and they go way over their limiting resources. So then there's a die off because they just don't have enough resources. So they go back to the carrying capacity, and enough of them die off, and they go back down. But then it starts to grow because again the population is low enough where they can thrive. They haven't reached that carrying capacity, and the limiting resource isn't used up yet. And again, it keeps happening and it oscillates, right? It oscillates, and it is an unstable equilibrium, meaning the increase and decrease won't necessarily be the same, but it'll continue to go up and down. And eventually that decreases, right? Because if your overall population decreases, then the change is going to decrease, right? So basically, understanding that exponential only works if there's like unlimited resources. That's not realistic. Just reviewing the concept of carrying capacity. There is another term here I had in my notes, biotic potential. I'm going to throw that out there too. Where was that definition here? So here it is. So biotic potential, maximum reproductive rate of a population in ideal conditions. So biotic potential is kind of like what occurs with exponential growth. So it just keeps going and going and going, but eventually, realistically, that doesn't happen, right? You reach your limiting resources. All right. So I think that's pretty good review with that. Make sure I'm not hitting anything here. Let's see. Another way, another thing we talked about with this, and I actually do have that links and hair chart, and that's the feedback loops we talked about with this as well. But that's the same concept there, right? So if there's a lot of hair, and then the lynx get to eat lots of hair because there's a lot of hair running around, eventually the hair population will decrease, and then the lynx population will follow. They will decrease because there's not enough food for the lynx to eat, and then it oscillates over time, and that relates directly to these oscillations, right? So let's say the hare overshoot, but then the lynx eat them up and they decrease, and then again the lynx will decrease and follow, so that it's basically a balance there between those, but that it's related to the overshoot and carrying capacity, right? So if there's too many prey, too many predator, things will they work together, and that's why this goes up and down. All right, hopefully that made some sense there. Okay. R selected, K selected. So K selected, low intrinsic growth rate, and it increased slowly until it reaches carrying capacity. R selected, high intrinsic growth rate, which often leads to overshoots and die-offs. And there you go. Lifespan for the K, long, short for the R, time to mature, long, short. Few reproductive, many. Few offspring, many. Large, small. Parental care present, absent. Slow growth, fast growth. Density dependent regulates. Density independent regulates. Stable near carrying capacity, highly variable, right? So K selected species. We talked about elephants, whales, humans, eagles. R selected are rodents, lots of insects. Let's see here, weeds, right? So invasive species tend to be the R selected. These also tend to be more generalist, right? Like again, I think of mice and rats. They can adapt to lots of things, whereas a whale cannot, right? Lots of birds are K selected species. Let's see. What we consider pests are selected in general. And again, look at the regulation here, density dependent, right? So density dependent, that's like food and water. And then density independent, that would be like the disasters, right? The natural disasters. And that's because these they grow slower, a lot of parental involvement. So community, a sense of community, and that would indicate if there's more of them, then the food becomes food and water becomes an issue there. Whereas here, they just as soon as they're born, they're fending for themselves, and it's not the same type of community. But that's a big difference there as well, and the dynamics are highly variable. But one thing that isn't here, I don't think it's on the next slide. No, is that again, these are generalist species, right? So invasive species tend to be R selected. That's why weeds seem to grow no matter what, whereas the actual like flowers or grass, let's say, won't, right? So all right, what else do I have here? Okay, real quick, survivorship curve. Here we go. 1, 2, and 3. Pattern survival over time, which there's a high survival through most of the lifespan, but then individuals start to die in large numbers as they approach old age. 2, pattern of survival in which there's a constant decline. And then 3, pattern is where it's low survivorship early, right? So type 1, you're going to live to a long age, and then die off will happen at the end of life. And then type 2 is fairly consistent. In other words, at any point in your life, there's an equal chance of dying. And then type 3, there is a lot of dying off very early. Survival is very low in type 3. So K selected are typically 1 and 2, right? So we are 1. And the whole point of that cemetery trip was, if you go back, it wasn't old enough. We had an older cemetery, it would work better. But if you go back in like the 1800s, it's more like a type 2, right? And especially if it's a time around wars, more type 2, because there's a higher chance of dying throughout your life. It wasn't advances in medicine and healthcare, for example, and nutrition, exercise, all that. Now we have advances in those things. We're not really fighting wars. So the quality of life is better. So we live longer and then die in old age, right? So that was the point of that. And then type 3 tends to be R selected because there's lots of early death for the type 3. So, I have mosquitoes and dandelions, and they have a picture here as an example. Apparently, squirrels are type 2. So that's it. I just wanted to kind of rip through that fairly quickly with you guys, just refresh your memory about those different types of survivorship curves. All right. So again, type 1, live long lives and die a lot of death at older age. Type 2, the chance of death is basically the same throughout the life span. And type 3, chance of dying early is very high. And that's again, very few individuals reach adulthood, and that is typically R selected. But because R selected have so many offspring, it doesn't matter, right? They're always reproducing, so that's why there's always a lot of them anyway, even though they die off young. All right, so there we go. All right, there's a video for you, and I'll kill it here. See you guys tomorrow.